Hello, welcome to a video on section 4.2 regarding the mean value theorem for derivatives. We're going to start these notes at the beginning of page 2. Since last time we met, we did discuss what the mean value theorem was all about and how now we're going to talk about how we're going to apply it to a particular problem here. We did talk about how the derivative will equal the average rate of change at a certain moment in your interval. And that's kind of the main point of the mean value theorem. Or geometrically, how the slope of the tangent line, or the tangent line itself, will be parallel to the secant line passing through your endpoints for some interval. So, for example 1, we have inverse cosine of x. And we're asked to show that it satisfies the hypotheses of MVT for the interval from -1 to 1. So the main thing here for part A is you want to show that y equals the inverse cosine of x is continuous and differentiable. It has to be continuous on the closed interval from a to b and differentiable on the open interval from a to b. We don't look for differentiability at endpoints, but we do look for continuity at endpoints. So, probably helps to graph the inverse cosine of x. You could use a calculator if you need to. The graph of inverse cosine of x is not painfully obvious, but the graph of cosine of x should be. We know the graph of cosine of x looks like that. Point at 0, 1, and a point at pi over 2, 0. And of course, there's a point right here at pi, -1. And as we know, inverse is when x and y switch. So now you're going to have a point at 1, 0. And now at 0, pi over 2, which I'll probably say is right there, and of course at -1, pi, which I'll say is right there. So that's, actually I could probably graph that a little bit better. It'll be a bit more curvy. Okay, so that's a graph of the inverse cosine of x. So just take the graph of cosine of x, which you should be familiar with, switch x, y coordinates, you can generate the graph of inverse cosine of x. Clearly, inverse cosine of x will be continuous on the interval from -1 to 1. Here's -1, here's 1, definitely looks continuous to me. Also, it will be differentiable because we should remember the derivative of inverse cosine of x, which is going to be this, -1 over root 1 minus x squared on the open interval from -1 to 1. If you plug anything between -1 and 1 into the derivative, it should be okay, right? You can square root 1 minus 0.5 squared, that's okay, or 1 minus 0 squared, not a problem. And of course not inclusive because then you'd have 0 at the bottom. So yeah, that shows that MVT is satisfied. Okay, now for part B. Part B is asking, find each value of c that satisfies that equation. Now, this is a big deal. Oh, I ran out of space. That's okay. Yeah, I can just maybe somehow push things down a little bit. and I'll probably have to create a new page for C and D. Okay, anyway, so you want to show f prime C equals this. Where A comma B, as we know, is the endpoints for our interval here. And we want to find C so that this expression or this equation is true. So basically, again, we have our graph, which looks like this, right? We'll call that A, we'll call that B. And of course, right there is a secant line, right? And the slope of the secant line is that expression, right? Average rate of change. Our hope is to find some tangent lines. Okay, I kind of missed. Okay, I missed again, but that's tangent. And okay, that's a little bit better. And that's tangent. So it looks like it's going to happen at a couple places. Where C is going to be some x coordinate, so that the tangent line to inverse cosine of x will be parallel to the secant line. Or basically the derivative, because the slope of the tangent line is the derivative, right, equals the average rate of change. So this is a kind of fun stuff because it's more calculus and math focused. So let's do it. So we're going to do f of 1 minus f of negative 1 over 1 minus negative 1. And f prime of C, or f prime of C, right? Well, f of 1 is easy. That's going to be 0 minus f of negative 1, which is pi, over 2. So, of course, we get negative pi over 2. Now, for our derivative, that's going to be negative 1 over root 1 minus x squared, or I'll call it 1 minus c squared instead. That'll just make things a little bit easier. So, negative 1 over root 1 minus c squared, negative 1 over root 1 minus c squared. So our job is to solve for c. What's the best way to do that? I would cross multiply. Negative 2 equals negative pi root 1 minus c squared. The negatives pretty much drop out, and I'll divide both sides by pi. Hopefully you can see the algebra here. And then I'm going to square both sides. And it's going to get a little bit messy because of the radicals in the pi. That's okay. We can handle it. 4 over pi squared equals 1 minus c squared. Out of space again. Okay. So kind of move things around a little bit. C squared put on the left side. 4 over pi squared put on the right side. C squared approximately equals, well, we know C is going to be the square root, plus or minus the square root of all that junk. Then I'll do an approximation. You know, this is what you should get in the calculator. So it looks like there's two different values of C that guarantee that the derivative equals the average rate of change. And if you look back at our graph, those C values right there, they look like they'd be about 0.771 or negative 0.771. And both are in our interval. So we're A-okay. So that's going to be the values of c that we need. And this is probably the most important part of the problem. Definitely you'll see something like this on the AP and next time we have a test, so it's very important. And you'll have some homework to help you with this too. Okay. Then you're asked to find the equation of the secant line. Well, that's easy. I can squeeze in C over here. Let's use a different color for contrast. Y minus y1, m times x minus x1. Of course, I could pick any point I want to be on the function. Let's say I use 1, 0. So I'll use a point 1, 0 since I know that's on the secant line. And the slope is right over here, right? Because that's what f of b minus f of a over b minus a is. It's the slope. So of course that's my equation of the secant line. Lastly, you're told to find the equations, right, it's plural, because we have 2 points of tangency, for the tangent line, and then to graph everything all in the same window. So I'll tell you right now for part D, if x is 0.771 for the inverse cosine of x, then y will be 0.690. And of course, if x is negative 0.771, y will be 2.451. And the slopes we always know is going to be negative pi over 2. So our equations for the tangent lines will be the following. Of course, to find those y coordinates, you have to use your calculator because it's doing inverse cosine of x. Okay, that's it. That's our answer for that. Then, well, not that's it, because we're also going to put all this in a graphing calculator. I'm going to try to see if I can use the graphing calculator app right here. Okay, hopefully you can see it. I can't really expand this, unfortunately. But if I were to graph inverse cosine of x, you could also do this in your calculator yourself. And make sure my mode is radians, which it is. And then, of course, I'm going to graph negative 0.5 pi x minus 1 and then I'm going to graph negative 0.5 pi x minus 0.771. That'll be plus 0.690 because I have to move that y coordinate over to the other side. And of course, negative 0.5 pi. Hopefully you can keep up if you're doing this on your own. Oops, that's supposed to be... Notice I just made a mistake. That's supposed to be plus. So how do we graph this? Let's check our work. Okay. Because minus negative 0.771. Hopefully, a few minutes ago someone was yelling at the screen while I was making a mistake. Plus 2.451. And then for our window, I think I specified to go from negative 1 point whatever. We'll just do negative 1.5 to 1.5. I'm going to go tick marks every 0.5. And y is going to be pretty tight. We don't need to have that wide of a y window. we go from 0 to like 4 because we want to see pi, right? And actually, what the heck, we'll do that in terms of pi and down in terms of pi over 2. Actually, I'll make that 1.5 pi. Okay, there's an inverse cosine of x. There's our secant line. And here comes our tangent lines. So we see that this looks pretty good, right? The tangent lines are parallel to the secant line. Happens in 2 places. You could even find points of intersection if you like. Now here I'm on the inverse cosine of x. I'm moving close to 0.771. Now I want to find the point of intersection with that line. No, sorry, that line. And actually I didn't quite get what we're supposed to get. Maybe I punched something in wrong. I don't know. But anyway, it should work. So, yeah, so let's move on. Oh, another thing too is that if you are solving something, you have to square both sides, like I did over here. You do want to check for extraneous solutions. You do want to make sure that the c values you get are legitimate, that you actually would get a y value that's a real number. Of course, inverse cosine of those numbers we're okay with, of 0.771, negative 0.771. So you want to be careful. Okay, so for example 2, you're asked if this ray drives continuously for 130 miles in 2 hours. Will there be at least one instance when its speedometer will read 65 miles per hour or 45 miles per hour? Now, as we know about MVT, that whatever value you have is going to equal the average rate of change at least once. So the answer is yes for both. And as for your reasoning, you want to apply MVT to whatever our position function is. And remember, average velocity here is 65 miles per hour. At least once will there be a time in this interval when s prime, or which is velocity, will equal f of 2 minus f of 0 over 2 minus 0, or which we know to be 65. And s prime being the instantaneous velocity, right? Likewise for b, but in this case we're really applying the intermediate value theorem. So, and we have talked about that before a while ago, but basically what IVT states is that as long as the position function is continuous, you will reach a y value between f of a and f of b for your interval a to b. We used IVT, you may have forgotten, but we used it to prove that something equals 0, right? We used to have these weird graphs and whenever it equals 0. But what we needed to do is we needed to find an a and b value that made a negative y and a positive y value. And of course 0 would be in between those two values. And of course, if we have a position function, we want to guarantee that, and here's our, so he has some sort of weird position function like that, and that slope is, or sorry, velocity function. And actually, I think that's what I meant to say, not the position function. Sorry about that, because we're not dealing with derivatives now, just the y values. So our velocity function was kind of like this. We're at 0, and that's 65. Of course, we're going to hit 40 at least once. So that's a and b for number 2. Some other things that are important to note is the whole concept of increasing and decreasing functions. So we can say that our function is increasing if we know for a fact that our derivative is greater than 0 in our interval. So in the case of this diagram right here, let me change colors for a bit of contrast. You know, right now, it seems like the derivative is positive, and it kind of stays being positive for quite a while. And of course, this function is increasing because y goes up as x goes up. Also, we can kind of see that our function is decreasing when our derivative is negative. So if we have these slopes of tangent lines that are all negative, this is clearly a decreasing function. You might remember this, talking about this in pre-cal, increasing, decreasing. If y is going down as x goes up, as x is going up, right? Y is decreasing. We see that our derivative is going to be negative in that interval. So that's kind of an important application of the mean value theorem, because we do see our secant line here, we have a positive slope. Our secant line would have a negative slope. And so, of course, we would anticipate that we have tangent line that's positive over here, and tangent line is negative over here. So again, if f is increasing our interval and x1 is less than x2, then we would anticipate that the y value at x1 is less than the y value at x2, whereas our function is decreasing when this happens. So again, if x1 is less than x2, then we would expect that f of x1 is greater than f of x2. So let's apply this principle to example 3. And I'll probably stop the video there and give you guys a chance to work on homework in class. And of course, when you don't finish, you could do over the weekend. Also because, okay. Good, it's still recording. I was getting a little worried there. So what you want to do for these problems is take the derivative, which is very easy, 3x squared minus 3, and we're going to set it equal to 0. remember, these are going to be our critical points, right? X equals 1 or x equals negative 1. And you're going to want to make a sign chart for f prime. Remember, we did sign chart to solve like quadratic inequalities or rational inequalities. You probably remember doing that in pre-cal, where you set some equation equals, well, actually, you have an equation really greater than or less than 0, and you want to see what makes the equation positive or negative for different values of x. So likewise, we want to see what makes the derivative positive or negative. We do know the derivative is 0 at negative 1 and 1. Of course, if I plug 2 into my derivative, not plugging the original function, mind you, plug into the derivative here, right? I know it's positive here, but x equals 0 will be negative, and of course x equals negative 2 is back to being positive. So we would see that f prime is positive in these intervals from negative infinity to negative 1 and from 1 to infinity. Also, we'd see that f prime is negative from negative 1 to 1. Notice I didn't use brackets. And actually, hold on a sec. No, I didn't use brackets just yet. But for my final answer, I will. So let me actually delete that because we don't need it. So for my concluding statement, I would say that f of x increases on this interval. Now I'll explain some more detail when I see you guys again, but you want to be inclusive when you're stating how it's increasing or decreasing, because it is increasing up to that point. Even though the derivative is 0 at negative 1 and 0 at positive 1, it is increasing up to negative 1. It's increasing at 1 and then forever to infinity. So you do want to put brackets there. And of course, f of x decreases in this interval from negative 1 to 1. And if you were to graph it, the graph's pretty easy. I did say we'd be able to do these graphs more accurately very shortly because now we've learned all this fun stuff with calculus. I know my x-intercepts are 0 and plus or minus root 3. So and anyway, I know the graph is increasing as we hit negative 1. And when x is negative 1, it looks like y is going to be 2. Yeah. And when x is 1, it's going to be negative 2. That's a pretty accurate graph. We have horizontal tangent lines in negative 1 and 1 because the derivative was 0, right? And we saw the derivative change sign. So this is something we're going to talk about later on, but this is what we're going to call, of course, a max and a min, because we saw derivative change from positive to negative at negative 1, and derivative change from negative to positive at 1, so that makes it a minimum. And we do see the derivative is definitely positive when we hit, from negative infinity to negative 1, and likewise from 1 to infinity. but then of course it's going to be negative between -1 and 1. So that's kind of the beauty of calculus, that we can make these graphs more accurately by using our knowledge of the derivative and applying it to these problems. So I won't do example 4. I think this video has been fairly long, and probably give you guys a chance to kind of practice doing some of these problems, and then of course we'll pick up these notes again. At least we're about halfway through the 4.2 notes, which we can wrap up when I see you guys again on Monday. Yeah, because we go G, A, B, C, D. Monday will be our last day before Thanksgiving break. Over break, I'll give you guys a video to watch on 4.3, and I'll ask you guys to do test corrections. I'll have the test back for you on Monday. And I hope you guys have a great weekend. I'm going to do a prediction for the Secant Prep Live Oak game. That is tonight. I'm going to say we're going 48-27. So Secant wins by 21 points, by 3 touchdowns. All right. Well, oh, and volleyball, we're eliminated, so I can't really give a prediction there. Water polo, I don't know. Yeah, we do have championships this weekend. Water polo, we win both. That's an easy prediction, but football could be a little tough. All right. Have a great weekend.